Hello students, welcome to lecture 16. From today on, we will study a class of machine learning algorithms called support vector machines. Support vector machines belong to one of the powerful class of machine learning models that can be used both for classification and regression tasks. In today's lecture, we will focus on the formulation and the definition of a linear support vector machine. We will cover the topics outlined here. First, we work through the formulation of a large margin separating hyperplanes and the support vector machines, and we will discuss why large margin separating hyperplanes are important in robustness of a hypothesis. Let's start with the pocket perceptron learning algorithm for a linear classification task on, for example, given a linear separable data as shown in this example. The PLA uses the following class of linear functions with a sign function applied on S. Here S is a signal which was equal to W transpose X, right? Finding this optimal perceptron hypothesis using PLA involves minimization of a 0-1 error function. The minimization of the 0-1 error is done using an iterative approach. Depending on the initial weight parameters, which can be randomly assigned, we may find different set of weights that minimize the same in-sample error in perceptron. In other words, there can exist different perceptron hypotheses which will bring in-sample error to 0, all with different parameters. For instance, in the following example, we see 4 data points. It's a binary classification task. The perceptron that we estimate from this data can be one of the 3 lines shown here. All right, all of which minimize in-sample error perfectly. We can also find other perceptrons that can separate all these points without any mistake. All these linear hypotheses separate all the points perfectly. And if we were to choose one out of 3, which one would be your best choice? Which hypothesis among 3 is the best one? Right? That's one of the main questions. One way to justify our choice is to consider the VC bound as a criteria, right? However, as we can see that in-sample error is 0 for all 3 perceptrons, 3 hypotheses that we have estimated from the data. And the VC dimension of all these 3 perceptrons are equal. Okay, so in-sample is equal for all of the 3. And also the VC dimension in 2D for perceptrons is same, right? And the VC bound for all of these hypotheses will be equal. Well, VC bound may say one thing, but surely our intuition can say that, all right, given 3 hypotheses, the rightmost separator is preferred. Why? Let's think about it. Can we somehow justify why the rightmost hyperplane is the best one or the preferred one? What kind of argument can support our intuition? Well, in practice, when acquiring data, there are usually measurement errors, which can be considered as a noise. If we draw identical shaded region around each data point, here in all 3 hyperplanes, with the radius of the region being the amount of measurement error, then the true data point, right, can lie anywhere within this region of uncertainty, okay, on account of the measurement error. A separating perceptron is safe with respect to the measurement error if it classifies the true data point correctly. That is, no matter where in its region of uncertainty, okay, in the following shaded region, the true data point lies, it will still be on the correct side of this separating hyperplane. A separating hyperplane that can tolerate more measurement error will naturally be safer, right? Where the rightmost separator tolerates the largest error because this shaded region is bigger. Whereas the leftmost separator, in this case, we can see that even a small error in some data points could result in a misclassification. Well, this separating hyperplane is better than this one because the shaded region is bigger, while the rightmost one is the best among the three given ones, right? The measurement error can be one of the main cause of overfitting, okay? Because we covered this as a form of stochastic noise, so data can be noisy. Well, regularization may help to minimize the effect of overfitting, okay? In our example, the rightmost separating hyperplane is more robust to noise because of the largest distance to the closest data, right? And we see that it still doesn't compromise in-sample error. In-sample is 0 in all cases. However, the rightmost one is we can call as a better regularized hyperplane or hypothesis. We can justify using this reasoning our intuition. We can also quantify noise tolerance from the viewpoint of the hyperplane separator. Let us place a cushion on each side of a separating line. This one, this, and this one, right? The cushion we put on the right side and then left side of the separating hyperplane. We call such a hyperplane with a cushion fat, and we can say that it separates the data if no data point lies within its cushion, within this region, right? Here, the largest cushion we can place around each of our three candidate hyperplanes are the third one, right? Rightmost one. And if any data point is perturbed by at most the thickness of either side of the cushion, it will still be on the correct side of the hyperplane. Okay? This motivates us that the maximum thickness is related to noise tolerance. Maximum thickness possible for a hyperplane is called its margin. Our intuition tells us to pick the fattest hyperplane possible. Okay, the one with the maximum margin. All right. So the robust separating hyperplane based on this observation should have fat margin. The margin that keeps the hyperplane far from both sides of examples. All right. Again, the robustness of this hyperplane is approximately equal to the fatness, right? In other words, the fatness again is a distance between this hyperplane to the nearest or closest data points, right? So can we efficiently find the hyperplane with the fat margin? Let's try to formulate the problem of finding a hyperplane with a fat margin. Recall that a hyperplane is defined by its weights. We want, okay, to find for example, the rightmost hyperplane from these given examples. Note that a maximum margin separating hyperplane has two properties. First property is that it separates all data correctly. In other words, the in-sample error is 0. All right. Second property, it has the thickest cushion among hyperplanes that separate the data. We can form the following optimization problem with the following objective function which we want to maximize. So find the weights of a hyperplane that has fat margin, all right, or the fattest hyperplane, subject to the hypothesis, classifies every point correctly. And the fatness of the hyperplane is equal to the minimum distance between hyperplane to the closest point. So the minimum distance is one of the three, okay? The distance from this point to the hyperplane. or from this point to this hyperplane. And again, we call the fatness of the hyperplane, this region, as a margin. And then correctness, this W classifies every x, y correctly, means the following, right? Y is equal to sign of your selected hypothesis, one of the three, should agree. So y is a given target value or the label in a supervised learning task for this example. So y is equal to sign of the dot product means correctness. Now, once we have defined these properties of the hyperplane that we are interested, our next goal is to find a separating hyperplane with a maximum margin. To find the separating hyperplane with maximum margin, first let us rewrite our optimization task or problem in terms of a margin. Okay, maximize the margin so that we no longer use the word fatness of the hyperplane. Okay, one more time, let me re-emphasize that we want to find this hypothesis with the maximum margin, subject to all points are correctly classified. Now, in this case, we represent correct classification as yn wtxn greater than 0, which ensures the correctness of the current hypothesis in classifying this example, this point. If y is -1, and then the dot product between w and x is negative, then it means that product of negative y with the following negative value would be positive. Thus, it is greater than 0, which means correct classification. If, similarly, the y is positive or +1, and then we have positive dot product here, then the product between +1 and then positive number would be greater than 0. All right? It is easy to verify. As we observed in our earlier intuitive discussion, the margin, okay, that is obtained by extending the cushion on both sides of the hyperplane is achieved until it hits the data point near the hyperplane. Okay? That is, in other words, the margin is a distance from the hyperplane to the nearest data point. Nearest data point. Not, for example, in this case, hyperplane, the nearest data point would be the one of two, or two of them. Right? So now we need to become familiar with the geometry of hyperplanes, in particular, how to compute the distance from data points, okay, to the hyperplane. Before we proceed with the mathematical formulation of the margin, let's fix a convention that we will use in the remaining parts of the lectures. First, we explicitly split the weight vector as follows, right? The bias weight, which was equal to W0, is taken out. And then the rest of the weights that range from W1 to WD remain as weight. So now we have W and then B, which correspond to bias. The reason is that the mathematics of large margin separating hyperplanes will treat these two types of the weights differently. All right, so to avoid any confusion, we already relabel W0 as B for bias, and we'll continue using W for the remaining weights from W1 to WD. And then we represent the hyperplane with the following equation. W transpose X plus B, where, again, the B, the bias, is explicitly isolated, separated from the previous weight. Okay? Initially, we coupled this bias W0 with artificial coordinate X0. Now we no longer need it. So our examples range from X1 to XD, W1 to WD. B is taken out. Let's next discuss how to compute the margin of any given separating hyperplane so that we can find the one with the maximum margin. To find the hyperplane with a large margin, we need to calculate the distance of x, b, and w, the point and then hyperplane b and w. And let's assume that our hyperplane is equal to the following equation. W transpose x prime plus b is equal to 0. Right? Let's consider a hyperplane as shown in this figure. Okay, in 3D. We can pick one point that is nearest data to the hyperplane. Okay, this is our hyperplane. We're taking this x, nearest point, and we'd like to determine the distance here. The distance from point to the hyperplane, which would represent the margin. Right? Let us pick 2 points on hyperplane that lies on hyperplane. X prime here and then x double prime. For these points on the plane, the following equality is true, right? W transpose x prime is equal to minus b. W transpose x double prime is equal to minus b because they lie on the hyperplane. We are using the following equality. Second, we must realize that the weight vector, this weight vector, is perpendicular to the hyperplane in x space. Since these 2 points, x prime and x double prime, lie on the hyperplane, they must satisfy the plane equation, right? So that W is perpendicular to the hyperplane as follows. So W transpose, taking the dot product between this vector, is equal to 0. This is the conclusion that the W is orthogonal to any vector that lie on the hyperplane, on the plane. I am referring to this as a hyperplane and plane, so they are equal definitions. And then now our task is to calculate the distance between x and then hyperplane. The distance between the nearest point and then plane can be computed by taking any point on the plane and computing the projection of the vector formed by, for example, x prime and x on w. This is w perpendicular, and then distance also will be a quantity perpendicular to the plane. So the projection of this vector onto weight will allow us to calculate the margin. In order to get this projection, we need a unit vector of w, or the weight. So we can normalize. So W transpose is a weight, and normalized by the norm of the weight will give us a unit vector. All right? The distance then will be equal to the following. We are requiring the absolute value. Okay, because the point can be on this side or on the other side, opposite side of the plane. And then absolute value will give us a positive number that again corresponds to the margins. And using the first inequality, we can just take the dot product between W transpose x, W transpose x prime, and using the following equality, we can simplify as follows. So W transpose x, and then W transpose x prime is minus b. So we plug the b, then we obtain 1 over W norm, and the absolute value of W transpose x plus b. So the distance to the separating hyperplane from the nearest point is equal to the following quantity, right? 1 over W norm, and the absolute value of this, W transpose x plus b. We have here in the product plus b. We know that the hyperplane defined by the weights W and then b separates the data correctly if and only if for every example in the data the following is true. Okay, the following inequality is true. So yn, and then the product between yn, the W transpose xn plus b should be non-negative. We have seen this before, right? For both positive and negative examples in the binary classification task, yn could be plus and minus 1. If both is positive, then they agree, that means greater than 0. If yn is negative and this term is negative, then okay, it's greater than 0. The distance to the separated hyperplane can be rewritten as follows, where we replace the absolute value of the following term of the hyperplane with the following. Our redefined optimization problem is now as follows. We want to find the hypothesis with the maximum margin, subject to all the points are correctly classified, and subject to the margin is calculated using the nearest point to the hyperplane with the minimum distance. Let us consider one of the hyperplane with a spatial fixed margin. Okay, note that the signal that we defined yn w transpose xn plus b also appears here is positive for each data point. However, the magnitude of the signal is not meaningful by itself because we can make it arbitrarily small or large for the same hyperplane by simply rescaling the w transpose and b. All right, so W transpose X plus B equal to 0 would be the same as 3W transpose X plus 3B bias, so B equal to 0. Okay, the scaling here doesn't matter. The magnitude of this signal doesn't matter. The condition here is that the sign of this condition, right? The sign of the signal matters more than the magnitude. Okay, so scaling doesn't matter. So we can consider, okay, spatial scaling, right, which results us or which gives us a separating hyperplane with the following minimum distance. So we can consider the spatial separating hyperplane where the distance is equal to 1. All right, minimum, the distance to the closest point to the hyperplane is equal to 1. This allows us to write down the margin as follows, 1 over W. Okay, so this is the minimum distance. If the following quantity will be equal to 1, the signal, then our margin will simplify to 1 over norm. We're now making our optimization even more friendlier, more simpler. So new optimization can be written as follows. So maximize the following objective function, which is equal to 1 over W, the norm of W, subject to every point is correctly classified, and another condition is that we are considering special case of hyperplanes with the margin equal to 1. Finally, we have the standard large margin hyperplane optimization problem. We want to maximize the following objective function, subject to that the minimum distance to the nearest point from the hyperplane is equal to 1. The necessary conditions for this optimization is as follows. Okay, for all n, which means again that we require all the points to be classified correctly. In the original constraint, we required a special hyperplane with the margin equal to 1, right? And wanted that the optimal b and w to lie inside the margin. However, if optimal, these weights, b, w, lies outside, we could scale to make it more optimal, which could lead to the contradiction as follows, right? If this is the weights outside the margin, which is equal to 1.126, we could scale it down so that it lies within this boundary. No, note that the margin is the inverse of the weight norm, 1 over W norm, right? We can do final changes as follows. Instead of minimizing the weight norm, we can equivalently minimize the following quantity, following objective, 1 over 2. So first, this is maximization. So to maximize this objective, we can minimize the norm of the weight. So in the first place, we convert maximization into minimization. So minimizing the following term will maximize the original objective function, right? So we change from max to min, first step. And second is we remove the square root that is adopted from the norm definition. right? And add 1 over 2 this constant, for that will be later useful, convenient, right? Therefore, okay, to find this optimal hyperplane, now we need to solve the following optimization problem, okay? So now not maximization, but minimize, find the W and B, but the B doesn't appear in the objective, but B appears in the constraint. Minimize the following quantities subject to the following constraint. The best way to get a handle on what's going on is to carefully work through an example and see how solving the optimization problem that we have finally derived as follows works or results in the optimal hyperplane with the maximum margin. Right? So in 2 dimensions, hyperplane again is specified by 3 parameters, 3 weights, W1, W2, and then the bias. Let's consider a simple toy dataset in 2 dimensions, which consists of the 4 data points, 0, 0, okay, 2, 2, 2, 0, 3, 0. All right, so x1, x2, x1, x2, for example, here. The data matrix here has a target values. This example, we label it as a negative example. This one has a negative, positive, and positive. Okay, binary classification task. Now we have the following separability constraints. Okay, if we use these separability constraints here, we will have 4 conditions. The first point, because x1 and x2 is 0, this will be, the first part will be 0. And we're left only the negative b, which is obtained by negative y multiplied with positive b, gives us negative b greater than 1, right? This one, so 2 to w1 negative, we multiply negative, and then negative 2 w2 minus b should be greater or equal to 1. This is, again, for each of these 4 examples, we require this constraint to be true. So we want to find the hyperplane with the large margin that separates all these points. Now, let us try to find the maximum margin hyperplane that satisfies these conditions. So by observing, we can see that for constraint 1 and then 3, the W1 should be equal or greater than 1. And then for constraint 2 and then for constraint 3, the W2 should be less or equal to negative 1, okay, which will lead to the W transpose W1 over 2 to be greater or equal to 1. We can also find that the optimal weights for the given simple example are equal to the following at a lower bound that satisfies all the conditions. Okay, but just plugging in W1 if it is equal to 1, W2 if it is equal to minus 1, B bias is equal to minus 1, then all the conditions are satisfied. You can plug this in, okay, these values in these inequalities and check yourself. Right? So the G, the hypothesis, the final hypothesis that you declare as SVM will be equal to the following. Okay, sine of x1 minus x2 minus 1. The equation of the large margin or separating hyperplane based on these examples. Okay, so W1 is 1, x1 times W1, we're just not showing 1, and plus x2 times negative W1, okay, minus 1, plus minus 1, right, which is equal to bias. So using this simple example in 2D, we found this as an optimal solution. And indeed, we can visualize these points. And then the decision boundary. So first point here corresponds to 0, 0, okay, 0, 0. So 2, 2, okay, this point corresponds to the x1, 2, x2, 2. 2, 0, 2, and then 0, right? 3, 0, 3, and then 0. Those are the points that we use to define the large margin separating hyperplane. We can eventually calculate the margin using those ways that we found using 4 data points, right? So the margin will be 1 over norm, okay, 1 over square root of 2, which is approximately equal to 0.707. Note that the hyperplane equation is shown here. This is the equation. Okay, x1 minus x2 minus 1 is equal to 0, which actually provides us the maximum margin, which is equal to 0.707 on 4 points. And if you look at the examples that define the margin, these ones, okay, and which are located on the boundaries, okay, we call them as support vectors, these points. And they play an important role in defining this margin, right? Hyperplane with a large margin. They are called support vectors in a sense that they support the hyperplane and prevent it from further expanding. Let's make again an emphasis that will be useful later. In this example, the margin is defined by 3 points. And the fourth point, if you remove this data point, which is not support vector, what will happen to the hyperplane? Nothing, right? The maximum margin hyperplane is found by using only 3. The hyperplane, if you remove this fourth point, remains same with the same margin. Even so, we remove that data point. Indeed, to compute the optimal hyperplane, only support vectors are needed, nothing more than that. The other data can be thrown away. Okay, when you work with the real-world data that probably has thousands of examples, only part of your data will be defined as support vector, which will define the margin. When we have a bigger data set, manually solving the SVM optimization problem, as we did in the previous example, is no longer feasible. It's not easy, right? Applying gradient descent based method could be one option. However, the constraints doesn't make it easy to solve these kind of constraint optimization using gradient descent algorithm. We know that the objective function we are dealing is a quadratic objective function of w and then b. Another good news is that the constraints are linear. We're dealing with linear constraint. We also note that the objective function is a convex function. Okay, convex problem has a good property that any local optimal is a global optimal. So they have only one optimal solution. The solution to the following optimization is unique and it is a global one. SVM's objective function belongs to a well-studied family of optimization problem known as the quadratic programming. Whenever we want to minimize this kind of quadratic and then convex function subject to linear inequality constraints, we can use quadratic programming solvers that the optimization field have developed. In order to use the quadratic programming tools, we will only need to know how to take any given problem and convert it into a standard form, which is then used by a quadratic programming solver. And we don't have to know how to solve a quadratic programming in software or the details of implementation of the solvers. All right. So in SVM, we have the following objective function. What we do is we pick one quadratic programming solver that is publicly available and then read its manual and form or rearrange all these so that it will, or convert all these so that the quadratic programming solver will take them as an input. Okay, that's the first step that is required. We need to describe the standard form of quadratic programming. So the variables, for example, that needs to be optimized are the components of the vector u here, okay, which has some dimension, let's say L. All other parameters, in this case, such as Q, P, and then A, and also C, for example, are user specified. And then the quantity being minimized also contains a quadratic term. This is a quadratic term and linear term. The coefficients of a quadratic term are this following matrix Q, right? Let's say some L by L matrix. And then the coefficients of the linear term also have the length of the vector. And we have M linear inequality. So the task is again, form a vector here as we form U as a bias, B, scalar, and then weight vector. We're forming a tall vector. And Q as the identity matrix, P. Okay, this we don't have the following term. We are using a 0. And the constraints are defined as follows: A, Y, okay, and then 1 over X. We're passing the data, and C, right? This step basically involves getting familiar with how the quadratic programming package requires the input to be defined. Okay. For example, solving the SVM optimization problem can be done in 3 steps using a quadratic programming solver of your choice. So the first step will be to convert the optimization problem into a standard form, which is then used as an input to the quadratic programming solver, right? Here, Q, P, Q is a matrix, P is a vector, okay, constraints. Second, all right, this step means running the quadratic programming solver. Okay, QP, you pass all those variables, and the output would be your bias and weight, right? The output of quadratic programming will give us the weights and the bias of the maximal separating hyperplane, which we can use them as a final SVM. We can declare this as GSVM, right? So note that in this formulation of the SVM that we have seen today, we only considered the hard margin SVMs, where data points are linearly separable. We considered the case only the data were separable by a linear function, right? In the next lecture, we will see that the SVM can incorporate a nonlinear mapping function to deal effectively with a linear or nonlinear separable dataset, which will make SVMs even more powerful. Let us recall why large margin hyperplanes are needed at all. A large margin hyperplane, we said, to be safe with respect to the measurement error, right? If it classifies the data points correct, that is, no matter where in its region of uncertainty, okay, the data point lies, it's still on the correct side of the separating hyperplane. So the large margin hyperplane can tolerate more measurement error, right? And is safer in terms of, again, overfitting. The measurement error, as we know, can be one of the main cause of the overfitting indeed. Well, we all know that overfitting can be cured using regularization techniques. That allows us probably to minimize the complexity of the hypothesis to fitting the noise, right? Resulting in overfitting. Again, why large margin hyperplanes? Why we care about this? So large margin hyperplane is more robust to noise because of the largest distance to the closest data point. And it still doesn't compromise in sample error, right? In sample is 0 always, we require that. So SVM optimization problem that we have seen today is similar to the minimization of in-sample error of, let's say, logistic regression subject to regularization or subject to panel. So regularized in-sample error, or we also said it, augmented error minimization, right? So in particular, here we minimize the weight in SVM subject to in-sample 0. So this is how SVM. So we are minimizing the weight that is somehow associated by or to maximizing the margin. While in general regularized problem, let's say, we minimize in-sample error subject to controlling the complexity of the hypothesis that is represented in terms of the weights, right? This is C acts as an upper bound on the weight growth. Growing the weight is controlled by C. This is a hypersphere. The SVM, in general, the optimization of the SVM can be interpreted as a weight decay regularization, since we are minimizing the quadratic weight subject to in-sample error. Going back to the concept of dichotomies, when we wanted to determine the number of ways in which a model could separate data in different configurations, right? Within a given linear model, we ignored the actual position and the angle of this line, the hypothesis that separated the data. We only cared for different resultant configuration, resultant labelings. However, if we did care about the position and the angle of the hypothesis or the line, we could say that the distinguishing factor of each hypothesis and the angle would be the margin error. That is the distance between the data it separates. Okay, if we cared about the position and angle of these lines. Right here, we're talking about, in this case, the perceptron hypothesis. Okay, so a higher margin of error makes it more tolerant to out-of-sample data. Again, due to the noise in the example. We can enforce a lower bound requirement on margin of the error, which naturally would result in less dichotomies. Right, as it places a restriction on the growth function, yielding a smaller VC dimension. In this case, if we compare the PLA that can shatter 3 points in general, the more restricted, or the PLA with the maximum margin, will be more restricted and will not be able to shatter any 3 points. This is the fewer dichotomies, fewer effective number of hypotheses, which result smaller VC dimension, right? So VC dimension is related to complexity or powerfulness of your hypothesis. So higher VC dimension, higher probability of getting overfit or for overfitting. While lower or smaller VC dimension leads to better generalization. Okay? Finally, let us compare 3 models to emphasize the benefits of large margin hyperplanes again. So here we have large margin hyperplanes. The hyperplanes itself, it could be perceptrons or linear models, or hyperplanes combined with a nonlinear feature map, nonlinear transformation. So in SVMs, in large margin hyperplanes, the effective number of hypotheses are very few. Okay, this number of hypotheses, dichotomies, let's say. While in the linear hyperplanes, that doesn't focus on that. While in linear hyperplanes, While in hyperplanes, the effective number of hypotheses are not many. While in hyperplanes, combined with the nonlinear transformations, result in many possible hypotheses. We can obtain many hypotheses that provides us small in-sample error. If we compare the boundaries of 3 selected examples of the model, the SVM or large margin hyperplane has simpler boundaries, right? Hyperplanes also have simple boundaries because, let's say, they are linear functions, while the hyperplanes with the nonlinear transformations can have complex, sophisticated decision boundaries. So not many effective number of hypotheses are good in terms of VC dimension and for better generalization that we know from the VC theory, right? So large margin hyperplanes provide even very few dichotomies. So sophisticated decision boundaries are good for working with data that cannot be separated with their linear functions, linear hyperplanes. Good for minimizing in-sample error. Okay? We will see later that a slight modification to the large margin hyperplanes or the support vector machines can result in a very powerful hypothesis with restricted effective number of hypotheses, but still having a sophisticated boundary and with a better generalization property as compared to the other two, the hyperplanes, hyperplane plus feature transforms. So this is a new possibility for deriving a nonlinear SVM. Okay, we will see that in the coming lectures. So the motivation of the large margin hyperplanes are that they are robust against noise and overfitting. All right, and then finding the large margin hyperplanes, we said, involves minimizing the length of the weight at a special separating scale. All right, that corresponds to maximizing the margin. And we said that support vector machines can be found using quadratic programming libraries because it has a convexity and then quadratic form of optimization. We also said in this class that the main reason behind large margin hyperplanes are that they have fewer dichotomies and a natural form of regularization that leads to better generalization. Okay, so weight decay could be related to maximizing the margin of the hyperplane. Well, in the next class, we will derive nonlinear support vector machines, which will be even more interesting and powerful. That's it for today.